Welcome to our first lecture in the world of nanoscience. Today we will begin by understanding what nanotechnology really is, why it matters, and how it connects to one of the oldest and most important ideas in science, the atom. Nanotechnology is the science of the very small. It deals with materials and systems that exist at the nanoscale, that is between 0.1 and 100 nanometers. To give you a sense of that scale, a human hair is about 80,000 nanometers wide. A red blood cell around 7,000 nanometers. But in nanoscience, we are interested in things even smaller, just a few atoms across. At this scale, matter behaves in surprising and powerful ways. Gold, for example, changes color. Carbon becomes stronger than steel. Reactions happen faster, and energy can be controlled more precisely. This is why nanotechnology is considered one of the most promising frontiers of science and engineering. Nanotechnology holds the potential to revolutionize fields like medicine, electronics, energy, and environmental protection. You have probably heard phrases like cancer-fighting nanobots, self-cleaning materials, small dust, or even molecular computers. Some of it sounds like science fiction, but the reality is much of this is either in development or already here. Still, to truly understand nanotechnology and to participate in shaping its future, we need to take a step back. We need to ask a basic but powerful question: what exactly is matter made of? And how small can we go? This brings us to atoms. Every application of nanotechnology begins with understanding the structure, behavior, and manipulation of atoms and molecules. Before we can build at the nanoscale, we have to understand the building blocks themselves. That is why in this lecture, we will first explore the history of atomic theory. We will meet thinkers like Democritus, who proposed the idea of indivisible particles over 2000 years ago, and follow the journey of this idea through centuries, through the work of scientists like Bohr, Dalton, Rutherford, Bohr, and into the quantum age. We will also look at modern tools like the scanning tunneling microscope that allow us not to see atoms, but to move them, arrange them, and engineer matter one atom at a time. You will see how IBM scientists use this tool to create the famous quantum corer, arranging 48 iron atoms into a perfect circle, and how that experiment symbolized the beginning of true atomic scale engineering. To dig a bit deeper, let us come back to the historical aspect of the evolution of atomic models. To understand how we arrived at today's concept of atoms, we have to go back to ancient Greece. Democritus, around 400 BCE, proposed that everything is made of tiny, indivisible particles he called atomos. His ideas were not accepted by Aristotle and were mostly forgotten until Epicurus and Lycurgus kept them alive philosophically. Fast forward to the 17th century, Pierre Gassendi revived atomism in a scientific context. Robert Boyle then brought physical reasoning into the picture with his gas laws. But the true shift happened in 1803 when John Dalton proposed that atoms are indivisible units that combine in whole number ratios to form compounds. This was the birth of modern atomic theory, and it set the stage for everything we now do in nanoscience. Now that we understand how atomic theory emerged, let us look at how our model of the atom evolved through experimentation. J.J. Thomson, who discovered the electron in 1897, proposed the plum pudding model. He imagined the atom as a sphere of positive charge with negatively charged electrons scattered within, like raisins in a pudding. This model was challenged by Ernst Rutherford's famous gold foil experimentation in 1911, his team fired alpha particles at a thin gold sheet. Most passed through, but some deflected dramatically. This showed that atoms have a dense, positively charged nucleus and electrons orbit it, much like planets around the Sun. Then came Niels Bohr in 1913, who refined Rutherford's model by introducing quantized electron orbits. He proposed that electrons exist in fixed energy levels and only jump between them when absorbing or emitting energy. His model successfully explained the hydrogen spectrum and laid the groundwork for quantum theory. While Bohr's model was a big step forward, it is still imagined electrons moving in neat circular orbit. But nature is more complicated. In 1927, Werner Heisenberg introduced the uncertainty principle, which stated that we cannot simultaneously know an electron's exact position and momentum. This shattered the idea of predictable orbitals. Then Erwin Schrödinger used wave mechanics to describe electrons not as tiny particles orbiting a nucleus, but as wave-like entities. His famous Schrödinger equation describes the behavior of these electron waves. This gave rise to the quantum mechanical model of the atom. Instead of fixed orbits, electrons now exist in cloud-like regions called orbitals, where the density of the cloud represents the probability of finding the electron. This is the model we use today in chemistry, physics, and nanotechnology. It is probabilistic, not predictable, but it is far more accurate. Now that we have talked about atoms, the building blocks of all matter, it is time to see how these connect to the field of nanotechnology. Interestingly, one of the earliest and the boldest visions of working at atomic scale didn't come from someone working in what we now call nanotechnology. It came from Richard Feynman, a brilliant and unconventional physicist back in 1959, long before the word nano had entered the vocabulary of science. Feynman gave a talk titled "There is Plenty of Room at the Bottom." He didn't use the word nanotechnology, but he described was exactly what we pursue today: manipulating individual atoms and molecules, shrinking machines to microscopic sizes, and imaging computers that could fit in tiny spaces. Ideas that seemed like science fiction at that time. In 1959, Richard Feynman didn't just deliver this very talk, he backed it up action. He offered $2,000 prizes to encourage scientists and engineers to explore the possibilities of working at atomic and microscopic scales. The first challenge was to build an operating electric motor that would fit inside a tiny cube no longer than 1/64 of an inch on each side. The second challenge was even more ambitious. Feynman asked, can someone shrink a page of text down by a factor of 1 in 25,000 linearly and still make it readable under an electron microscope? Just a few months later, William McLellan, using nothing but tweezers, a microscope, and a lot of patience, built a tiny motor with 13 parts that met the requirement. It weighed just 250 micrograms and spun at 2000 revolutions per minute, a remarkable achievement, especially considering this was done in 1960. 26 years later, the second prize was claimed by Tom Newman, a graduate student from Stanford. Using electron beam lithography, Newman and his colleague Ken Polasco managed to write the first page of Charles Dickens' A Tale of Two Cities at a scale that entire paragraph fit on the head of a pin, exactly as Feynman had envisioned. While Richard Feynman imagined the concept of atomic scale engineering in 1959, The word nanotechnology itself was not used until 1974. It was introduced by Norio Taniguchi, a Japanese researcher, in a paper titled On the Basic Concept of Nanotechnology. He described it as processing of materials one atom or molecules at a time. So even though Feynman didn't use the term, his vision clearly laid the foundation for what would later be called nanotechnology. By the 1980s, the word nanotechnology was being widely used in research and industry. One of the strongest advocates was Richard Smalley, who won the 1996 Nobel Prize in Chemistry. In 1999, he told the US Congress that nanotech could change our lives as much as microelectronics and medical imaging together. Today, nanotechnology is often called the next industrial revolution. It is all about rearranging atoms to build entirely new materials and tools, one tiny piece at a time. This is the famous Lycurgus Cup from the 4th century AD. Believe it or not, it is made using nanomaterials, glass embedded with gold and silver nanoparticles. When light passes through the cup, it looks red. When light reflects off it, the cup looks green. This color change happens because nanoparticles interact with light in unique ways, something we now understand as plasmon resonance. So if nanomaterials were already being used nearly 1600 years ago, what is the big deal today? What is different about modern nanotechnology? The Romans had nanomaterials, but they didn't know it. It was purely accidental. Today we can design nanomaterials with precision, targeting exact sizes, shapes, and properties to create new functionalities. That is the real difference and why nanotechnology is now a deliberate, powerful science rather than an accidental art. When we talk about nanomaterials, the first image that usually comes to mind is nanoparticles. But nanomaterials can take many different forms. The key idea is that even if one dimension of a material lies between 1 and 100 nanometer, the material behaves like a nanomaterial. For example, in thin films, the area may be very large, but if the thickness is in the nanometer range, they are nanomaterials. Similarly, nanowires may be very long, but their diameter is in the range of 1 to 100 nanometer, making them nanomaterials as well. And then we have atomic clusters, where all the dimensions are smaller than 1 nanometer. These are called zero-dimensional nanomaterials. Together, these examples show the different kinds of nanomaterials beyond just nanoparticles. Now that we know how nanomaterials are classified, let us see how they are used in real-world applications. Magnetic storage media use nanostructural layers to pack more data into smaller spaces, making devices faster and more efficient. Super hard materials like nanostructural diamond or boron nitride are much tougher than their conventional form due to their fine grain size. Optical tweezers use laser light to manipulate nanoparticles and even biological cells without physical contact, essential in research and diagnostics. In biomedical applications, nanomaterials can deliver drugs directly to the targeted cells, improving treatment precision and reducing side effects. And in nanotextile products, nanofibers and coatings make fabrics more durable, stain resistant, and even capable of advanced functions like sensing or camouflage. These are just a few examples. Nanostructural materials are impacting industries from electronic to healthcare and defense. Here is the first wonder of nanostructuring, surface area enhancement. When we take a large particle and break it down into nanoscale pieces, the total surface area increases dramatically. This simple effect is one of the main reasons why nanomaterials behave so differently from their bulk counterparts. More surface means more reactions, more interactions, and more functionality.